That's the whole point, and we can break it down.
Well, in this case, let's just...
Let me get in the middle.
This argument.
Go on.
So it has been argued, it's been argued that because the universe had a beginning, therefore God. And I'm saying...
Content over everything!
That argument doesn't work. Now that doesn't mean there is no God, but if you're using that as your argument for God, then that's a bad argument.
Alright.
Okay? And we were talking about, can we... So one question why that's a bad argument is we don't know whether the universe had a beginning or not. Okay? It may have done, I'm not saying it didn't.
Well, we must question it, that's the point.
Absolutely.
Exactly.
We don't know. Okay?
Perfect.
Now, some people, and this is the argument that we are having, are trying to say, well, we can be confident that the universe had a beginning because of thermodynamic arguments. No, not because there was a creator, but because of thermodynamic, because of the thermodynamic arguments. And I'm saying those thermodynamic arguments don't work. Okay, that doesn't mean there's no God. There could still be a God. Doesn't even mean there's no beginning. There might still be a beginning. It just means that that particular argument doesn't work.
Makes sense.
We can only address one argument at a time.
Of course. Of course. And that's why I disagree with it.
Okay. So go ahead with your
should we do it again for the camera? Like just very brief.
Yeah, that's fine.
Very brief. Just for the camera.
Yeah. Okay.
You
want to
on
do it again?
Are you rolling? You're
rolling, yeah?
Okay, who wants to start? You want to start?
We're here.
You can start.
I'll start. Okay. So there's a very famous argument of why people should believe in God. And that is because the universe must have had a beginning because of something called the second law of thermodynamics. And basically, the second law of thermodynamics says that, and he's going to disagree with this, but I'm going to put it my way, and he can always change. He can always put it his way.
Yeah, his point, of course, yeah.
Is that entropy always increases as time goes on. So if entropy always has to increase, that means there has to be a beginning where there was zero entropy, where at the start, or at least very low entropy, where the beginning of the universe had to start. So that's the argument.
Okay, can I give the response?
So,
very.
Okay, you ready for the response? Okay, so first off, yes, I am going to disagree with the definition of the second law. The second law doesn't say that entropy always increases.
You're not going to look at the camera?
Sorry. Okay, sorry.
Do your thing.
That's fine. Okay, so what the second law says is that entropy is overwhelmingly more likely to increase. But it's not impossible that entropy can decrease. In fact, if you have an infinite amount of time, it's absolutely guaranteed that the entropy will decrease. Because even the smallest probability is guaranteed to happen as long as you have a long enough period of time. Okay? So actually you don't even need an infinite amount of time.
Can I ask you a question?
Okay. Well, hang on, one thing at a time. Let me just respond and then we'll do your question.
Let's just do us two
and then you can weigh, right? Okay. So the entropy argument actually logically doesn't even work just on that. Okay? Now, I don't think, though, that a spontaneous decrease in entropy is a reasonable explanation as to why the Big Bang was in a low entropy state. We do agree the Big Bang was a very low entropy state. However, what we don't know is why it was in a low entropy state, and that's a mystery. Okay, so many physicists, and I've interviewed many of them, have proposed dynamical explanations as to why the entropy was in a low entropy state. One example that we gave, and you can watch my film on the YouTube channel SkyDivePhil, look at our film on conformal cyclic cosmology. This is just one proposal of many. Okay, Roger Penrose has suggested that there was a pre-Big Bang universe. The entropy of the universe, if you count, and this bit isn't controversial, that if you count out the entropy of the universe, most of it's in black holes. Okay, black holes are believed to evaporate. The controversial bit, or one of the controversial bits, is what happens to the information when the black holes evaporate. We have two main theories in physics: general relativity, and that says the information goes away. Quantum mechanics says no, the information doesn't go away. And we don't know. Both of these theories are very well verified by experiment, so we don't. But they conflict. They conflict. So we don't know which of these answers is correct. Penrose lands on the relativity side. No surprise, because he's one of the world's experts in relativity. Okay, and if you watch our film, he'll make his case for it. And if that's true, then the entropy will disappear when the black holes disappear, and that would be one example of a dynamical process that would lead to a low entropy Big Bang. Now there are other people, other cosmologists that propose other solutions. One is that the total entropy of the universe is actually infinite. There is no maximal entropy.
Phil, can I stop you? Is it possible you can give one argument?
Okay, fine.
Fine.
Yeah. Okay, fine. Okay, so that's my argument. The bottom line of the argument is We don't know why the Big Bang was in a low entropy state, and it's certainly conceivable they were.
You're giving one possibility.
What created the low entropy state was some dynamical process, and therefore it doesn't show that the universe had a beginning.
Okay, so first of all, let's deal with this, your first point, and that is that entropy does not say that, the law of entropy doesn't say that entropy will always
Second law of thermodynamics.
Yeah, second law. Second law.
Specific.
Yeah, we'll do it. We'll do it specific. We'll do it specific. Why not?
I like that. Go on.
Why not?
Because the first law is going to give you a problem.
No, it gives you a problem, not me.
Okay.
The second.
All right. Okay. All right. Anyway, go on.
The second law of thermodynamics, right, in my opinion, does say that the entropy will always increase, and here is why I think you're wrong. So, first of all, why is it only say Phil's saying it tends to increase because of the nature of the mathematical model is probability. So basically, because of probability, therefore, by definition, there must be possibilities where it can happen, where it decreases. Right? It must be. However, what Phil is confusing is mathematics with science. Let me explain this out. Let me flesh this out. So, for example, in science, right, when you make an experiment, right, if you, let's say take gravity, for example, if you want to know the laws of gravity, so you say, okay, I come up with these laws, and you make experiments to see if these are the laws.
Back up this law.
Yeah. Now, the amount of laws that you're going to make is going to be limited. So let's say you make a million experiments, or a trillion experiments, right? You can never make an infinite amount of experiments.
Right.
So
definitely,
when you've made all those experiments, you're always going to have the same results, right? Which is the laws of gravity, right?
Drop this, it drops. Fair point.
Yeah. So now, when you have, within that we say it's a law, right? That things fall. We don't say things tend to fall. We say that things, two bodies attract each other. We don't say they tend to attract each other. Okay,
True.
and the reason is because science and mathematics don't work the same way, right? If something always works in a certain way, right, when we're testing it, right, then we say that is the law, right? Now, it could be, right, that the universe is in such a way that sometimes it doesn't, right?
Okay.
But the way science works is we make the law according to what we say always happens. Now, if you go back to the second law of thermodynamics, right? The probability of it going the other way, or reversing of entropy going lower is so low. It's really difficult to. Do you want to give a little bit go to give a feeling of the numbers?
I feel science, man.
But they're astronomical. I mean, I mean, obviously.
You know, actually, I have one.
I mean, they're obviously astronomical numbers.
Okay.
No one's disputing that.
Yeah, but I want to give a bit of a feel for the people that are watching. Give a bit of a feel.
Okay, go on.
So,
I feel science, man. Don't get too scientific. I'm joking. Sorry, I'm joking. Carry with your point.
But when you agree it's a finite number, the probability of entropy going down is a finite number.
Yeah.
All right?
So the probability of entropy. The probability of entropy going lower is so small that basically, if we'd be if we were doing experiments, right, all our lives, and every single person was doing experiments, the entropy will always go up, right? I'll try and give you one small taste of how extreme this law is. So, for example, if you had a box of air, right? Not like a 1 centimeter big, right? And you ask a question: what's the probability of all the atoms, all the molecules going on one side, right? Let's say the left side, right? The probability, and that's really a very small thing. Right? The probability of that happening is so low that if we were testing like every second for the whole universe, and you had trillions of these boxes, the whole universe was full of these boxes.
But it's a finite number, though.
You would never. The chance of it happening would be so low that would be close to impossible. Basically,
but it's close. The difference is
it's close to.
My point
it's the whole point.
No. But my point is,
it's so vast.
But why is it important that it's so vast? Why is it important is
because you can go on forever. Up to some extent.
Let me say.
Alright, go on.
It's because in science, when you're doing any experiments, you can't do infinite amount of experiments.
Agreed.
You're always going to do a finite amount of experiments. So really, every single law of science is going to have the same thing, where we don't know that if we did an infinite amount of experiments, maybe you would find exceptions, right? So really, trying to use a mathematical model to try and say that this law is not really 100%, it's not absolute because of mathematics.
So let me understand your argument.
Let me just land. It's incorrect because you're using mathematics on something which is science, and when in science we don't work that way. We work according to the way how something we always, if we measure it and it's always that way, then that is the law. That's the way science works. I don't think you confuse science with mathematics.
Okay. So I agree with you. I agree with a lot of what you said. Okay, but I think the conclusion that you reach from what you said is false.
No conclusions. I'm just saying
no,
separate.
Okay,
I'm just saying you can't say.
No, okay.
But I'm making a single point.
All right, let me try to make this point. Okay.
I'll see you in a minute.
Okay. All right. So I agree with you that you can only do so many experiments. However, I think where you're going with this contradicts your very argument.
Don't worry about what I'm going with it.
No. But let me try and see
when we get there. Let's worry about it then.
Okay. So what you're saying is, it seems to me, if I understand your argument correctly...
Don't straw man me.
I'm not straw man.
Wait till I make my own arguments. Okay, go on, say it. He's like telling me what I'm going to say, so...
No. Okay, all right. I'm just trying to conclude from what you have said already, okay? So, from what you've said already, it seems to me what you're saying is, you accept that entropy can go down, but we're not going to observe it. And we can only go with what we observe.
I'm saying that's science. That's how science works. All laws of science work that way. That's
okay. So what you're saying is we cannot extrapolate beyond our observations.
I'm saying that.
Is that what you're saying?
No. Well, I think that's.
I think that's a logical implication.
I think that's a logical implication. But what I'm saying is.
Okay. Well, let me make my point there, right? So therefore, if that's the case, if we say we can't extrapolate beyond what we can observe, well, we cannot observe what happened at the Big Bang. Right, at the moment, there's no observational evidence. So we cannot make a statement it was the beginning or was not the beginning. Because if you're going to say we can't extrapolate beyond our observations, then you can't make the statement as to what happened at the Big Bang. Right? You just can't make that statement because by your own rules, you're not allowed to extrapolate beyond observations. And at the moment, our observations only give us a cosmic microwave background.
My point is not...
They don't tell us what actually happened at the moment of the Big Bang itself. And they don't tell us why the entropy was in a low state. So you have to basically say nothing about that. So therefore, any statement, the universe had a beginning or did not have a beginning, by your own rules, is an illegitimate statement because you're extrapolating beyond what you can observe.
Look, here's the thing.
So either you can extrapolate beyond what you can observe, or you can't. Right? Or maybe you can with less confidence. But you seem to be extrapolating beyond what you can observe and then saying no one else is allowed to do that. And that's inconsistent.
Well, before we get there, you first have to deal with your claim, right? Which is that it's not a law that's absolute. So I would ask you have to use the same logic to deal with all of science. Would you say that all laws are not absolute? You're the one that's bringing this up.
Okay.
I'm not the one that's bringing it up.
Well, first off, I think
I didn't say that the laws. I'm saying according to you. According to what you're saying.
No, I don't
it's
think
it's absolute. I the opposite. I said it is absolute. I didn't say it's not absolute. I said it.
Well,
my point when you say something's absolute, we're talking about in context of our experience. That's what I'm saying. I'm not saying you can or you can't extrapolate. That's not my argument. My argument is how science works. Science works not as mathematics works. That's what I'm saying.
All right. So the way I see science working...
And therefore what I'd ask from you is, I'd have to ask from you that you should be consistent, right? When you say about other laws in nature, would you say the same thing? That they're only... That like you said, they're tentative, they're only, you can't take them out of the context.
Okay, so with respect to laws, first off, it's not what I say. Anyone can look this up. Go and look up what the second law of thermodynamics says. Okay, it is different to other laws because we actually know a little bit about laws. There's still stuff we don't know about laws of physics, but there are some things we do know. And one is how we actually derive certain principles in physics. So for example, conservation of energy, local conservation of energy is derived from what are called Noether theorems, okay? So Emmy Noether was a very famous physicist, and she derived things like conservation of energy, which is the first law of thermodynamics, from what are called symmetry principles. So you can derive conservation from time asymmetry. So basically, the past is like the future in a very particularly well-defined way. So these laws are derived from symmetry principles. The second law is derived from something called state counting. Okay, and so we don't, like, things don't have like a label that say how much entropy they have on them. Okay, it's not like I put an entropy thermometer on you and I come out with a reading that says how much entropy is there. That's not, as I understand it, how entropy works. It's based off state counting and atomic theory. Okay, so from our understanding of that theory, that tells us that the second law says entropy is not guaranteed to always increase, but is overwhelmingly likely to increase. Yes, there's stupendous numbers, no one's disputing that, okay? But that's our understanding of the law. And now when we do science, what we want to do is, if we should make statements about the world that have a given level of confidence based on the given level of evidence that we have. So where we have overwhelming evidence for something, we have overwhelming confidence in it. Okay, we can still revise that. Now, as to whether the universe had a beginning or not, we don't. Well, hang on, let me come to the point.
You haven't answered the question. You haven't answered my question, which is, would you say that all laws of nature are not absolute?
They may. I think we don't know the answer to that. That's my answer. We don't know.
So we don't know that they are absolute. So we can't say that they are absolute. So really, when you're saying the laws of gravity, you can't say that they are. You know, this is the law of gravity, because we've never tested infinite amount of times.
Right? No, but we don't need necessarily to do that. For example, let's take conservation of energy. That's the first law of thermodynamics. Agreed? Yeah. Okay. Energy is always conserved. Okay. Now, would you say that's absolute? Can never be violated?
Well, I have a different model of how I'm answering. Okay, let me give an example. Because when you talk about
hang on. Let's.
Okay, I would say no. I would say no. But
no to what?
It's not absolute.
Okay.
It's not absolute.
All right.
Yeah.
So how can it be violated?
So I wouldn't call it violated. In fact, actually, my opinion is that the second law of thermodynamics works very much like the first law in this way. That is probability. Let me explain why. Okay. So, for example, in quantum mechanics, right? So you have things popping into existence and they go out.
Vacuum fluctuations.
Fluctuations. Quantum fluctuations. So basically, the only reason why things don't suddenly pop into existence is because the probability of it happening is all equal. Okay. So on average, you're going to have always the same amount of energy. So even though, is that your understanding? Same.
Yeah, I agree.
I agree. So the first law of thermodynamics is just as much a probability as the second law of thermodynamics.
Okay. There is a difference, I think. Because what you in quantum mechanics, what you have is you measure the whole state. You will see teeny tiny fluctuations in energy.
Yeah.
Agreed. But those are within a certain system. When you talk about macroscopic molecules, you don't see that.
It's the same. Okay? It's the same as second law of thermodynamics.
Well, I think there's a subtle difference. I mean,
where's the difference? Show me the difference.
Well, I think the difference
you have a belief there's difference, but show me, give me an example, how's different?
Okay, well, I think the difference is that in the second law, you are using purely classical systems, okay? So from that perspective, there is a difference. No, but okay. So there is a classical deviation from the first law as well, actually, but that's from the expanding universe. So if you have a universe that's expanding, then you actually violate time translation symmetry. So you don't need to concern yourself with quantum fluctuations.
Time translation symmetry. What is that?
So that's how we derive the first law of thermodynamics. The first law of thermodynamics is derived from Noether theorems. All right. So that basically says that there's a symmetry between the past and the future. That doesn't mean the past and the future are identical, but there are certain symmetries that give you conservation of energy. And in an expanding universe, then you can't actually specify those symmetries, and you can break those symmetry principles, and you don't specify conservation of energy in general relativity and cosmology. In fact, you have a violation of, well, it's hard to define what is conservation of energy in general relativity. You really only talk about it in local systems. Okay, so that's a classical way to do it. But anyway,
they break down. They break down a certain.
All right, yeah, we're agreed on that. Okay, we're agreed on that. We're kind of going off on a tangent.
Yeah.
Okay, so we agreed that these laws may allow for exceptions. Okay, So
it's not that they allow for exceptions. Except, like, look, I think it's actually quite easy to understand if you think about it in if you
hang on, can I just make one thing?
Yeah,
you haven't really addressed the point that I've made. And the point that I've made is, as we don't know why the Big Bang was in a low entropy state, right? We're not in a position to say it must have been the beginning of the universe, because it's perfectly reasonable to think there were dynamical processes that put the entropy into a low state. Furthermore...
so that's your second point. So right,
no, that is my main point.
Well, your first point was about that the entropy never is not absolute. That's your first point. That's what we're talking about now.
No, that's just about how we define the second law. That's not my argument. Okay. My argument is really about this: is that since we don't know why the Big Bang was in a low entropy state, and since it's certainly conceivable that there were dynamical processes that put the entropy into a low state, then we can't say low entropy at the Big Bang guarantees the universe from the beginning. We just cannot make that statement.
Okay, this would be my argument.
Okay.
I try to do a complicated one. I think I've got a simpler way to argue.
Okay, go ahead. Yeah.
Okay, so if you've got entropy, it's very low.
Yeah.
Which means you can. Order is not a good way of describing low entropy, but we're going to use it for the moment so we have words to use.
Yeah.
Okay, fine. So basically, you got a lot of order. Let's say 100 pieces of order, so to speak. Okay, obviously there's no such thing as pieces.
It's fine. Yeah.
100 units of order, so to speak. Now, when some of that order goes into the black hole, goes into these black holes, you're going to have 50 of them. It's going to go to the black holes. When those 50 black holes go away, you're only left with 50. And then each universe that you make, that gets created or comes into existence, is going to have less and less and less order, right? So there's no.
So you're saying is there is residual entropy that doesn't.
I'm saying if it's true. I don't agree necessarily.
No, cool. I mean, we're just using this as a toy model, really.
Yeah. So if it was true that, I mean, you don't know it's true either.
No, I'm not claiming it's true.
Right. So, but I'm saying if it was true, what would happen was these units of order that I've just made up would go less and less and less. So if there was infinite amounts of universes, we would end up with no entropy, with a very high entropy, no order.
Okay. So let me address that point. So in as I understand Penrose's model, what actually happens is there's what's called a conformal transformation. Okay. So to try and explain what a conformal transformation is, conformal geometry is a type of geometry that doesn't care about scale. So if you think of the angles of a triangle, they add up to 180 degrees. Okay, if you double the size of the triangle, it's still 180 degrees. So this is what we call conformally invariant. Okay, so the argument that he makes, I mean, again, you have to watch the video to go the real details. Okay, and read his papers if you want even more details. Okay, so the argument that he makes is that the entropy, so you have a conformal transformation at the Big Bang because there's no matter left in the universe. Okay, if there's no matter left in the universe, effectively the whole entropy score is reset, if you like. Okay, so there's no entropy coming through from the pre-Big Bang to the post. I mean, the bottom line is, let's put it this way. If you have a pre-Big Bang universe and a post-Big Bang universe, how do you know that the entropy of the previous universe goes through into the post-Big Bang? I mean, that's really what we're talking about here. I'm only using Penrose's model as a toy model, right?
So how do you know that it goes through? What do you
exactly.
mean?
How do you know?
The question.
Okay, well, let's put it this way. You've got X amount of entropy in the pre-Big Bang universe, let's say.
Yeah, let's say 50, let's say 100.
Whatever it is, okay?
Yeah.
Now, the question is, as you go through a transition from the pre-Big Bang universe to the post-Big Bang universe, how do you know any of that entropy is going through? How do you know?
Oh, I'm not suggesting it is.
Well, if it isn't, then you can't use that argument, can you? Because let's suppose none of it goes through into the post-Big Bang, right? There are certain things that are not going to survive the transition. A star, for example, is never going to survive the transition from pre-Big Bang universe to post-Big Bang universe. Okay.
I think
so the question is then.
I understand what you're saying.
Yeah.
I understand what you're saying.
Okay. So respond
I
to
just
that.
don't think anybody that's watching will understand.
Okay. So let me try and explain it a bit. So it's certainly conceivable that there was a pre-Big Bang universe. Okay. Many models of quantum gravity, many popular cosmology models assume that. Okay, we don't know if they're right. It's still unknown at the moment. If there was, okay, they will have some entropy. Okay, then the question is, how do you know that the entropy is going to survive that transition? If it doesn't, that will be again a dynamical explanation why the Big Bang was low entropy, and it would not prove the universe could not be eternal in the past.
Okay, so Phil, what you're doing is, I think you're confusing percentages with amounts. So, for example, if no entropy, right, goes to the next universe, right, then you're going to end up with a new universe, which is a very, very low entropy. Let's say 0, whatever, close to 0. Let's say, for example. But that doesn't tell you how much energy, right, is there for there to be entropy of. So, for example, let me give you an example. Let's say there's 2 rooms. Okay. This is different. It's not connected with the previous example. Okay. No connection. I just thought about this on the spot. Okay. So you have 2 rooms. Okay. One room has a canister in it. Okay. And this canister is 10 liters. Okay. Right. Okay. And it's full of a lot of gas being very highly pressurized in it. Okay. And you have another room, right, which only has a canister with half a litre. I have a feeling most people don't understand what we're talking about, but continue.
Well, maybe you try and simplify the argument.
Okay, I'll try and simplify the argument. Okay, so if you got these 2 rooms. Now, in both rooms, the entropy, so you've got it's a vacuum. Both rooms are vacuums, and the canisters are pressurized containers, right? So in both rooms, the entropy is very, very low, right? It's 0 because there's no air within the room, okay? You agree, right? But even though both rooms have an entropy of 0, right? You still have different amounts of energy within each room, right? You can use a lot more. There's a lot more energy you can use in one room than you can use in the other room, even though they both have the same amount of entropy, which is 0. Do you get what I'm saying or not?
Carry on. Why don't you just go to the conclusion, and then we'll try and review.
So therefore, if you have one room, right, when it goes to if the entropy goes down, and you're using let's say you're using from one room, you're using 10 volts of energy. I know we're cross-pursing electricity with pressure, but never mind. Let's say you're using, it goes into electricity for whatever reason, and what's the name of the pressure unit? What's the pressure unit? Pascals? I think it's Pascals.
Well, the pounds per square inch.
I think that's what it is. Okay. So let's say you got 1,000 pounds per square inch in that canister, right? So let's say if you use 200 pounds of that, right? You will still have energy to be used. There'll still be entropy will not be 1, will not go complete yet, right? Whereas if you use the same amount of energy in the other room, right, all the energy will become balanced, right? Okay. So in other words, it's not just so entropy is a percentage. It's the amount of energy that can be used within the system to do work, right? Okay. It doesn't tell you how much energy is within the system. So, if you're constantly, every time you have a universe, right, so I'm going back to now the example, which is the universe. So each time you have the universe, more and more energy is going to be used up, and it's going to be turned into entropy.
Okay, that assumes,
then even though you're going to have 0 entropy from each universe, you're always going to be having less and less energy that you can use.
Okay, I disagree. Okay, I think that's just wrong.
Okay, why do you think that's wrong?
Because you're assuming conservation, you're assuming the first law. You're assuming conservation of energy, okay? If you can have increases in energy, you can violate the first law in an expanding universe.
So now we're violating the first law.
Absolutely. You have to, right? If you have an expanding universe, you can't talk about the conservation of energy anymore. Think about it, right? How much, if you take vacuum energy, okay? Vacuum energy, agree, is not 0. Do you agree with that?
Vacuum energy is not 0.
Agreed?
It's total. It's 1. Vacuum. What's vacuum energy? I thought you were talking about entropy. What we talking about?
If you have a vacuum, does it have any energy in it?
I think so, I guess, because you got.
Oh yeah, it does. Yeah. Okay, I mean we've measured it.
Yeah, well you got waves can go through a vacuum. Yeah.
No, we're not talking about waves going through a vacuum. Empty space has energy.
Yeah, I've heard that, but I don't know what it means. So I don't know.
Well, if you're going to dispute,
I'm not disputing it.
Many famous physicists.
I'm not disputing it. I'm just saying I don't know what it means. That's all I'm saying.
No. Okay, if you're going to, this part of what I'm saying is non-controversial.
I'm not disputing it.
But energy conservation.
But if you don't know what it means and I don't know what it means, then how are you going to use it for an argument?
This is not controversial.
I'm not saying it's controversial.
Okay? Energy cannot. Conservation of energy only applies what we call locally, i.e., where the expansion universe is not felt. Okay, that's just accepted in cosmology. That's the fact. All right.
What? Say again. Conservation of energy only works when
it's locally. It doesn't work. You can't talk about conservation of energy globally for the universe.
Okay, so hold on a second. So let's stop there a second. Can I stop you there a second?
Yeah, sure.
Okay, so you got a universe. Imagine it's this big, right? And then it expands. Okay, so now all the matter in that universe and the energy of the universe has gone out. So surely you have a conservation of energy.
No.
Why not?
There's two things that happen. Well, first, one of the things that happen. This is where your misunderstanding of vacuum energy is very important. Okay.
Yeah, maybe because
okay, I'll just try and explain it. We discovered, for example, that the universe is accelerating its expansion. Okay. So that means that when
that's a theory. It's not a fact.
No, that's an observational.
Accelerating.
Yes.
Expanding. Yes.
And accelerating.
That's an observation.
Yes.
That's not what I read recently. Okay.
Where did you read? No, this is important. How can you not know this? This is won the Nobel Prize in Physics. It's on the cover of every single.
Not as a like.
No, as an observation.
As an observation that it's accelerating.
Yes.
Okay, you have to show me off the camera. Show me. It's not.
No, this is important.
Is it part of the?
Yeah, it's part of the.
Okay, go on.
I mean, I'm just amazed that you don't know this.
No, because I read differently recently.
Where did you read?
I can't remember. I have to.
Okay. I mean, this is like, if you want to follow physics, cosmology, then I suggest.
I think. Roger Penrose. I read recently that Roger Penrose argues that there's not an accelerating universe.
Roger Penrose, Thailand.
No,
that's
nonsense.
what I just read.
I had lunch with Roger Penrose only a few weeks ago. I made a film with him. His whole theory is based on the fact that it's accelerating in its expansion. So no, he does not say that. That's nonsense. Okay, you can watch my film with Roger Penrose.
Hey, Shalom, how are you?
Shalom.
Okay, you can go on YouTube. Okay, and maybe I can get.
Wait, let's get this clear. You're saying that that there's evidence.
Yes. That the universe is accelerating in its expansion.
That the universe is accelerating. There's evidence.
Yes.
Do you know what that evidence is?
Yes, I do.
Okay.
Okay, I tell you what the evidence is. Okay. You can look at well, there's a couple of things, right? One, the first one is looking at distant supernovas. Okay. Because supernovas, as we understand them, that in certain cases there are different types of supernovas. But certain supernovas explode with a known energy, okay? And if they explode with a known energy, then, well, if you want to know how far away something is, all you have to do is know how bright it is, and then how much brightness how bright it is intrinsically, and then what brightness you measure it as. Because let's suppose I've got a light here, suppose that's a light, okay? You're going to measure a certain brightness, okay?
How do you know how light is intrinsically?
Okay, we'll come to that in a second, right? If you know how light it is intrinsically, then if you go further away, it will be less bright, okay? So you have to try and work out then how do you know it is intrinsically.
So if it goes half brightness by 5 minutes away, you know it's 10 meters away.
Exactly, right. It falls off as a square of the distance, right? Okay, so so with supernovas, because we understand how a certain type of supernova goes off, we understand the physics of it, we can say how bright it is intrinsically, okay? Then we measure the brightness and then we can infer the distance. And because in cosmology, when you see very distant objects, you're looking back in time billions of years, you can then work out what the expansion rate of the universe is. So you can see how fast was it expanding in the past, how fast is it expanding in later times, and then you can see is it accelerating, decelerating, or staying the same. And measurements show that it's accelerating. Not only that, we can also measure the geometry of the universe. So we can draw. If you draw a giant triangle, add up the angles. If you draw the triangle on a flat piece of paper, it's 180 degrees. Okay. If you curve the paper, the angle of the triangle will no longer be 180 degrees. Okay. If it's positively curved or negatively curved, you'll get deviations from 180 degrees. So what you do is you look at the very oldest light that you can, which is a cosmic microwave background, And what you find is that if the universe is flat, you will see a certain pattern in the cosmic microwave background. And if it's positively curved, you see a different pattern, negatively curved, another pattern. Okay? So then we look at the cosmic microwave background and we see that it is flat. Now, if it's flat, that means the energy of the universe has to add up to a certain number, okay? So in fact, it's 1, right? So what happens is, you can add up the mass of the universe.
What does that mean, the energy?
Okay. So what it means is you can look at how much mass there is in the universe, and how much visible matter is, how much dark matter there is, and what you see is an enormous deficit. There has to be something else in the universe, some other energy. Okay. Okay. Right. So now this is generally considered to be the dark energy. Okay. Or cosmological constant, perhaps. Okay, so we've got 2 independent measurements that tell us that the universe is accelerating in its expansion. Now, what does this all mean? Why is this all relevant? Because when the universe is accelerating in its expansion, then that vacuum energy that is causing the universe to accelerate in its expansion has a constant density, okay, which is a violation of conservation of energy. And if you don't like the acceleration of the expansion of the universe,
I'm not saying,
as an example, we can also just...
I gave my argument. I just say that's what I read.
Well, what you read is incorrect.
Yeah, okay, fair enough.
And we can also just take the normal expansion of the universe, because of course what happens is the light, the cosmic microwave background, gets redshifted. It cools down, so it loses energy. Where does that energy go? Well, nowhere, right? I mean, it just goes. That's a violation of conservation of energy.
Isn't that confusing the second law with the first law?
Well, this is, if you like, as I said, the first law is conservation of energy.
Yeah.
That is what the first law is.
Yeah.
Okay? Your argument assumed that there has to be conservation of energy for the universe as a whole. That's I think, the logical implication of your argument.
No, it's not my argument. It's just what I thought.
Okay.
Yes, it is.
It is, right?
Yes, it is.
Now, what I'm saying is that's not correct. On the scale of the universe, energy is not conserved. It just isn't. Right? You can't write a conservation of energy law for the large-scale structure of the universe. That's just not correct. Okay? So your argument doesn't work.
Okay, so I'm going to have to research that because
that's fine.
So let's leave it there.
If you want to research, you want to check it for yourself. There's a good blog post by a cosmologist called Sean Carroll. He actually wrote a very popular textbook on cosmology and gravitation. It's what most people that study general relativity, or I don't know most, a lot of people will say, oh yeah, get the Carroll textbook. He has a blog, it's called Preposterous Universe. Go on his blog, Preposterous Universe, and he has a blog post saying energy is not conserved in an expanding universe. And if you don't believe that, I have a video.
I'll research it, so
okay, but I'll show you a video. It's about 30 seconds long. Okay, I can put it up for you right now. You won't be able to hear this, I'm afraid.
No.
But this is an interview I did.
It's best to put the link to just say what it's called.
Okay. I'll show it to you, and we can put the link on the video.
I mean,
right?
You can always give me later.
I can give you the. Well, it's not. I haven't posted it yet. I'm making a video with a very famous cosmologist at the moment. His name is Niayesh Ashfordi. He's one of the professors at the Perimeter Institute for Theoretical Physics, and this is what he said about conservation of energy. I don't know if you can hear this.
There's no point in me doing it in this. I've got to do it properly.
Well, we can talk to each other. It's not all for the video, right?
Well, I'm going to need time. Okay, go on. I need to do it not in the part. I've got to do it properly. That's
fine. Of course you do. But this is just for the moment.
What is the video?
Well, he is, I guess. Is this your video?
No, it's not mine. It's
right. Well, then why do you care about whether it's a video or not?
I don't know if I care. He's saying the same thing as you're saying.
Right.
I'm going to need to look into it.
Yeah, of course you do. You shouldn't take my word for it. I'm not an expert.
Yeah,
I interview experts.
I don't think you made it up. I don't think you made it up.
Right.
I don't think you made it up. That's not my
I'll give you
point.
another source. So you should never take one source.
Hey.
Okay? Never take one source.
But I would actually question it though, because if you Phil.
Yeah, I'm listening.
Okay, here's my question on that. So supposing you've got a universe this size, right?
Yeah.
And you got all the energy spread out in the universe, just for a simple model sake, yeah.
Hang on, let me interrupt you 1 sec. This is a website. This is a blog post. Energy is not conserved. right, on this blog post. Sean Carroll, and look, his actual web page is the second law. He's one of the world's experts on this topic.
I saw Sean Carroll. He's talking a load of rubbish.
You check it.
I saw one video. He's talking. You know what? Let me give you an example of something that claims to be science, right? And then when I've looked into it, it's not science at all. Okay. It's just hypothesizing. Okay. I'll give you an example. So it was Richard Dawkins, and if it's really somebody else, forgive me, but I'm pretty sure it's him. Yeah. So he gave a model of the universe, it's basically expanding and then contracting, and he gave the reason, and then he said it was wrong. And then he said the reason why he gave that model was because he was using a sphere, right? And the way a sphere goes, it goes up and and then it expands and then it contracts if you're going around the sphere. So he had no evidence for that. He was just using a model that he thought maybe matched the universe, but he had no evidence for it. That's not science. That's just. It's not even hypothesizing. It's just like, well, maybe this. It's like an idea. It's like, you know, maybe it's fried chicken, maybe it's this. It's not science. So I'm not saying yours is not science, but I'm just saying I'll check it out and we'll take it.
Okay. There's some things that I've said that are controversial models, and I don't claim them to be correct. Other things that are consensus. Yeah. So the Penrose model, that's a controversial model. It's speculative.
Yeah, you said so. You made
I'm not claiming and making any claim that it's true. I'm just giving it as an example, right? The conservation of energy not being true at a global scale, that is not controversial. Okay, that is accepted.
It's something new. Okay. I'll check it out.
Okay, great. Now, to reply to your thing about what is science and what is not science, I mean, I think speculation is part of the scientific process. But what we need to distinguish between scientific facts and scientific speculation. I think speculation is part of the scientific process.
Oh, that's semantics. I have no problem calling it that. Yeah,
right. So what I consider a fact is something that has overwhelming evidence in favour of it.
Yeah.
Okay. So. Yes, the idea that the universe is cyclic is speculative. But we don't know whether it is or not. It might be, it might not be.
But not really, because if you would test the second law of thermodynamics, right, there'd be overwhelming evidence for it. But because we know the mathematics behind it, now we're saying that it's not a fact. It's only something that's most likely to happen. Sorry, I just wanted to bring that out because.
Well, now we're going around in a circle. You're making the same argument we did before.
No, because
we're going round and round in a circle.
Okay, you know what? Forget that. I want to actually bring a new thing. So finish off with
go ahead with a new thing.
Okay, so what I'm going to say is we're moving a little bit philosophy now.
Okay, fine, I'm fine with
that.
And then I may have a wonder, because there's someone I'm looking for in the park, by the way. We can come back, but go ahead. Yeah. Let's do this one and then we can move on, that's fine.
I
just need to check my phone as I'm waiting to see if someone is trying to contact me. Yeah, go ahead.
Okay, but it's a continuation of what we're talking about. Mm-hmm. Okay, so basically, when I say I believe in God, right? From a physics perspective, right? I'm not talking about something positive, right? I'm going to need to flesh this out a little bit, so it might need to be 2 minutes. Okay, so for example, people that claim that they believe that in the laws of nature, right? So the laws of nature basically are just limitations. The law says it can only work in this way, right? Whereas,
go on with your point. I'm not sure I agree with that.
Let me finish it, and then you'll address the points that you need to address. Okay. So a law says that this has to work in a certain way, right? And I know the second law, so ignoring the details, ignoring that kind of stuff.
That's fine.
Okay. And basically, my version of God, when understanding in the context of evidence from a physics perspective, is just all it's saying is that there's no laws. That's all it's saying is.
Okay.
So any laws that you claim to exist ultimately don't exist, right? So that's where it's not my only understanding of God. So for example, I understand it from biology, there's also a mind. But from a physics perspective, all my argument is that there's no laws, ultimately, okay? So, something infinite that has it's not limited in any way, okay? What my problem is when you give these arguments is that the law itself, or the second law of thermodynamics, right, is you're modifying it. You're saying it doesn't apply, or it doesn't apply in this way, it doesn't apply that way. And I agree with you. Like, for example, mathematically for sure, it doesn't ultimately in an infinite universe will not apply. I agree with that. But that kind of leads into what, in my view, is that ultimately there are no laws, and really what these laws are really analogous to a computer, where the laws are just they don't have to be that way, they just are that way, right? And I would argue that they're created that way, but I would argue that ultimately there's no laws. A computer doesn't start off with laws. You program in the laws, so to speak, and so yeah, that's
okay. So I mean, I think we just don't know what the status of physical laws are. It could well be that they do have to be how they are, that there's no logical alternative. Now, I don't know. I mean, it might be, there could be many different ways. I think we don't know. We don't really know the status of the laws in the sense of, are they just descriptions of the way objects behave, or are they something more than that?
But you do know, you said they break down. The first law breaks down, the second law breaks down.
No, we're talking about ultimate laws. So with the way the universe
But how do you know there are ultimate laws?
No, so when we talked about, well, okay, there may not be. I mean, we just don't know.
Okay, but the laws that we do know, according to you,
break
down.
Okay.
So why do you believe there are laws?
No, okay. So for example, conservation of energy is tied up with time translation symmetry, okay? Now the question is then, why time translation symmetry? And to that, you know, we get to these points where we go, we don't know beyond that, okay? We just don't know. And I'm happy to just leave it at we don't know. And if we can increase our knowledge, then great.
I'm talking about what we do know.
No, but you aren't, because you're saying there are no ultimate laws, and we don't know whether that's true.
You're right.
That's an assertion that I don't see any evidence for. There could be ultimate laws.
Of course.
We just don't know.
I agree with you, but my point is that, okay, let's put it this way. The way I see it is, if you're saying that there's no God purely from a physics perspective, from those arguments perspective, what you're arguing is that there are laws. Do you agree with that or not really?
Well, when you say law, I mean, I think we all agree there are laws of physics. The question is, what is there? Are there ultimate laws that can never break down?
That's my question.
I don't know.
No. But
it could be.
Okay, let's put it this
there
way.
aren't any ultimate laws, or maybe there are. I don't know. Either way, I think we just don't know.
I understand that. No, I understand that. But what I'm trying to say is, let's hypothetically suppose that we did know, for hypothetical, that there was no laws, right? Do you understand that is what I'm calling God?
I agree. I think the definition of God is more than that.
No.
That may be a part of. I mean, I agree that people that believe in God generally don't think that there are laws that govern his behaviour.
Right.
Agreed?
Okay,
but however, some people do. I mean, some people think the laws of logic constrain God, that he's not allowed to make a logical contradiction. That's a difficult. I know you don't necessarily believe that, but many theologians think that God is constrained by the laws of logic.
We can't argue with ghosts, so you know what I mean?
No. But I'm saying is,
okay,
fine, that's fine. So you think that there's nothing that constrains God, even the laws of logic don't constrain God.
No,
so he could make a logical contradiction.
No. Sorry, is that what you're saying? No, the opposite. I say that God cannot go against logic.
Okay, right. Okay. Well, that is what I was saying.
Oh, okay. Sorry.
Okay. All right. So there are some kind of laws that are above.
No, I disagree with you.
Why not?
Because I don't think that's about following a law. I think that's simply about semantics, about what we're creating in our words. We're creating logical contradictions as though something exists. It's not something that exists. For example, if I said God can create everything, right? Or God can do anything. So you give any example that you can give, you say God can do that, right? When you say can God create a stone that's too heavy for him to pick up, all you're doing is you're just creating a logical contradiction. Right. You're not actually creating anything that he can't do. Do you understand what I'm saying? So, well, anyway, that's the way I see it. In short,
let's get to the point. The laws of physics, at least, don't constrain God. He's above the laws.
Yes.
That's what you're saying.
Yeah, of course.
Okay, maybe there's a being in the universe that isn't constrained by laws of physics. Maybe that's true.
No, that's not.
But what evidence is there that is true?
That's not the point. That's what I'm trying to say.
What is the point?
Well, my point right now, you're probably rushing off. But
let's come to the point, and then we'll try and finish it.
My point is, first, simply that if you believe that there are constraints, then you would be an atheist. Within the arguments of physics, not any other arguments like experience or biology or anything else, but purely from physics perspective, right? If there are laws, then you'd be an atheist. If there are no laws, then you'd be a theist. Does that make sense? You're purely from physics.
I think.
If. I know we don't know.
I appreciate what you're saying. I think if you think there are laws that are ultimate, then nothing can supersede, then you can't be a theist, right? But you could be a deist, right?
Okay, yeah.
But you're not necessarily an atheist.
Right.
Now, if you think the laws change, right? Let's suppose you think that laws change over
saying
time.
If there's ultimate laws, you could be a deist?
Yeah.
No, I disagree with that. Well, let's not argue that. We're just.
Fine. All right. Okay, well, that's fine.
Agreed to
okay, fine. Okay, so you could take the view. Lee Smolin is a well-known physicist that is proposing that the laws change over time. They don't have any constancy. They just change over time.
So according to that, is the ultimate laws or not?
Well, there might not necessarily then be any ultimate law. All laws just change.
Why bring?
Are subject to change.
Okay, go on.
But then he's not a theist, as far as I know. He's not claiming this is anything to do with God. He's claiming, in fact, that the universe is infinite.
Well, we don't know if he believes that there's ultimate laws or not. Number one. Number two, we don't know.
Well, as far as I understand, as I understand it, right? He's not claiming there's any ultimate laws. But no, I'm saying is logically, you could take the view that there are not.
From your perspective, from my perspective, let's forget about other people.
No. But what I'm saying is, this is an example of someone that doesn't believe in ultimate laws and doesn't derive God from that either.
The problem with giving these examples is that they might be mistaken.
Well, of course they could be mistaken. No one knows, right?
Of course, not that.
I live in the street and I need some help.
Sorry?
I live in the street and I need some help.
Sorry, I've been told the best way to help people is not giving to beggars. That's the advice I've been given. I'm sorry. Right. So, okay. So the point I'm making is, you could take the views. If you took that view, right, the laws just change over time, maybe randomly, right?
That's not what I'm saying. I'm not saying that he
you're
doesn't
not necessarily led to God.
I'm not saying he doesn't know whether they change or not. Of course he doesn't know. That's not my point. My point is he might not have thought through the logical arguments.
Okay,
he might not have thought through that if there was no laws, that would be equivalent to a theist using...
ultimate.
Yeah, no ultimate. Sorry.
No one's claiming there's no law.
Yeah, of course,
right.
There's no ultimate laws.
Yeah.
That he might not necessarily understand that would be equivalent to a theist arguing God purely from a
well, let's suppose you take the view. Let's suppose
he may not know that.
Robert, but the reason I think he wouldn't know that is because I don't think it just doesn't follow. It does not follow.
So forget about him. Tell me why you think it doesn't follow.
I'll tell you why I think it doesn't follow. Yeah. Suppose you imagine that the laws just change randomly over time. That's it, right?
So are there ultimate laws or are they no ultimate?
In that sense, I don't think you would say there were any ultimate laws. But that doesn't lead you to God.
Oh, I see.
Right?
Okay. But there are always laws. There are always laws. But maybe. So when we mean laws, you know,
I think what we
let's ignore the third example. Just out of the two examples, would you agree?
What I'm saying is,
would you agree that if there is an ultimate law, right, that would be atheism? Where if there's no ultimate law, forget about drifting laws.
No, but this is important. I don't think you can forget about it because suppose. Okay,
because
let's see what we agree on. Let's see what we agree on. I agree that if there's some ultimate law, physical law, that cannot be broken by any being, that rules out God.
Right, we
agree on that.
Okay.
So now let's take the opposite case. If suppose that there are no ultimate laws.
Yeah, and no moving laws.
No. But if you have, suppose, no laws of any kind.
Yeah, no.
Suppose there's pure randomness in the universe. Everything that happens.
No, it doesn't mean there's randomness. Just because there's no ultimate laws doesn't mean it's randomness.
Well, it depends what you mean by law. I mean, to me, a law describes a behaviour of an object that doesn't change. Okay?
Exactly.
Right.
Exactly.
So now you could have a state of the universe where things just were entirely random. Nothing is connected to anything else.
Stop. One has nothing, just because things, okay, you're confusing two separate things.
I'm not.
Okay, I'll tell you why you are. Saying that there's no ultimate law doesn't mean that there's randomness, right? Let me give you an example.
No, it's the other way round. Suppose you have pure randomness. I agree with that, but you're misunderstanding my point.
Oh.
Suppose you had pure randomness.
Oh, then there'd be no.
Then there's no laws. There's no laws, right?
Oh,
you couldn't write down a law. But they can't infer, therefore, God from that.
But we know that the universe is not, so that's irrelevant.
No, we're talking purely hypotheticals about nature of laws at the moment.
No, but let's talk about the fact that we live in this universe.
Well, okay, hang on, but one thing at a time, right? You're saying you can infer...
That's not hypothetical of that there's no universe.
No, we wouldn't be claiming there's no... It could be the universe was in a state of pure randomness. Okay, and then laws emerged from that.
But
of course it's not now. Of course it's not now. No one was claiming now. We're talking about what is logically possible. Okay? So, yes, of course, this isn't what we observe now. No one's claiming that, right? We don't observe God, do we? So if we're only restricting ourselves to God, we rule that out too. Yeah? So my point is, you could imagine a state where there are no laws and you still you would not necessarily be led to the point that there is a God from a state of no laws, no ultimate laws. Okay.
If you had randomness, okay.
Right. There we go. So we're agreed.
Yeah. Okay.
All right, cool.
Okay. But
I'm going to have a quick walk around the park because we ended up on an agreement, and isn't that sweet? Okay. I may come back. Okay. But I'm looking for 1 or 2 people.
Okay. Enjoy.
Come take over everything from your melody.
Man, say it straight. Man, don't listen to BBC. Man, don't listen to ITV.
So yeah, guiding the new generation. That's what we want to talk about. Is that what we want to talk about? How the best way to do it? Yeah. What's the best way you do it? How do you do it? How do you do it? No one said that was a way to guide the new generation. We got a bit confused now. Yeah, it's like a man goes out drinking and he said, "Well, that's not the way to be in the Labour Party. That's not the Labour manifesto." No one said that it was on duty 24/7. Like, what is it you think guiding the new generation is?
Well,
maybe I need to correct you.
Camera acting like that.
How can you tell me I shouldn't shout?
What's he talking about?
I shouldn't shout.
Who are you to